Today's lab is to show you how to use the stress transformation equations shown here in the picture. We start with a stress block in our original coordinate system, as we see here on the upper left, and ask how would our components of stress change if we rotate the stress block at our same stress state by an angle of theta. The angle of theta is defined as a counterclockwise rotation from the original coordinate system to the deformed coordinate system. A clockwise rotation would be a negative angle theta. The relationship between the stress components in the rotated configuration and in the original configuration are simply described by the equation shown here at the bottom. So you see, all we need is basically the state sigma x, sigma y, and tau xy in the original state, and the rotation angle between the two coordinate systems. If we have that, then it's a straightforward equation just to plug in. Let's explore the equations on a simple example. Let's look at the 1D stress state shown on the left side, where that stress state is rotated as shown here. We want a stress block oriented traditionally with horizontal and vertical orientation. So I described the original state with a coordinate system x and y, here shown in green, and I need a coordinate system for my target system. That's what I want to call x prime and y prime. I'm looking first at the rotation angle. The rotation angle goes from the original x to the final x prime, which is in our situation a rotation that's counterclockwise. That means the theta value must be a positive number. The next step is to identify the given components of stress. In order to do so, I draw the positive components of stress that are consistent with the coordinate system x and y that I've drawn here. That shows here now sigma y, sigma x, and previously tau xy. Next, I compare those to my given stresses, and we see that the 10 ksi are actually a positive sigma x. So we have sigma x is 10 ksi. There's no shear stress or normal stress in the perpendicular direction. That means sigma y and tau xy are 0 ksi. At that point, I know all the components of the original stress tensor. What I'm really interested in are the components of stress in the rotated system. That's my x prime and y prime. So I mark them here in red at sigma x prime, sigma y prime, and tau xy prime. So once I have those, given my original values sigma x, sigma y, and tau xy, and given a rotation angle theta that we haven't specified any further at that point, I am ready to use the transformation equations from the previous page. So what do we have here? On the left side of the equations are our unknowns, new components. On the right side, the red markers, that's the stress state that we have. So let's start with sigma x. Sigma x was 10 ksi. Let's put the 10 ksi everywhere where we had sigma x. I just skipped the ksi here because there's just no space. So the 10 wherever we had sigma x. Next, we identified sigma y, so we replace everything where we have sigma y. That's simple, it's simply 0 ksi. And the same story follows with tau xy, which was also identified to be 0 ksi. Once we have those values, we need a rotation angle theta. And let's just, for this example, assume a rotation angle and say theta shall be 30 degrees. The sign's given simply by the drawing because we are going counterclockwise. It's a positive number. So all we have to do is wherever we have that rotation angle, we would have to replace this. I do it here even for the values where we had 0 ksi just to show that these components are always present. So there's nothing special about the 1D state of stress given in the original problem. We can simply plug in wherever we need it. The important message here is actually that while the original state was a 1D state of stress, after the rotation, we see that we will have components sigma x prime, sigma y prime, and tau xy prime. That means the rotation created a full set of numbers that in our case is really simple to compute. And I just finish here by writing up all the equation what's left, so the non-zero components. I leave it to you to plug in the numbers in your calculator. That's always a great exercise practice, because you don't want to waste time later on at an exam or in the job. The only thing here that's left to do after you do the calculation, do not forget about the units. We did the calculations with input values in KSI, so the output values will be in KSI as well.